let V be a unit tangent vector and G sub T be a geodesic flow. Our objective is calculating the Hausdorff dimension of the set of fellow traveling vectors W for a given V. Explicitly, the distance between the 2 points and with a geodesic should be bounded by large R. So we didn't get the bounds on the dimension yet, but we found some sufficient conditions for W to fellow travel around V. So W should be in this set using continued flexion expansions. So here is the definition of continued flexions. So let X be a real number between 0 and 1. And this X can be expressed as follows. So when I say A1, A2, A3, and da, this means continued flexion expansion of X. So X can be represented by a sequence of positive integers, AI. So the Gauss map is a map defined on open interval from 0 to 1 as a decimal part of the 1 over X. So if you draw a graph of 1 over X, then it will be like this. And you take the decimal part, so this part goes down, this part goes down, and then the graph would be like this picture. So let's examine the properties of Gauss map. So when you take inverse to the continued flexion starting from A0, then it becomes A0 plus continued flexion starting from A1. So the decimal part of the inverse of the continued flexion starting from A0 becomes a continued flexion starting from A1. So we see that the Gauss map T can be seen as a shift map. So in this shift map, the start is from, from the left, it starts from A0, while from the right, it starts from A1. So the sequence shifts. So the Gauss map can be seen as a shift map. Okay, here's a hyperbolic plane. We'll use the upper half plane model for the hyperbolic plane. So hyperbolic plane would look like this. And the Riemannian metric on this plane would be given as dx squared plus dy squared over y squared. And there's a boundary. This dotted line is a boundary, and also there is an infinity point. So this R and the infinity point should be called the visual boundary. You can think of geodesic as just length minimizing curve for now. A geodesic on this hyperbolic plane is either a vertical line, this one, or a half circle which is perpendicular to the boundary, which is in the right one. The blue lines are the geodesics here, and let's move on. So here's a definition of geodesic flow. A geodesic flow on a manifold is a map from unit tangent bundle to itself, which describes the geodesic. For instance, let V be a unit tangent vector on the hyperbolic plane here. Then this geodesic flow GT sends this V to GT of V, which is an evolution of unit tangent vector along geodesics over time T. So let wait a second. V be this one, and then GT of V would be this one, while this length, hyperbolic length, would be T. Now, isometries on the hyperbolic planes are described by Mobius transformations. This map F, it sends Z to AZ plus B over CZ plus D, where the determinant of this matrix ABCD is equal to 1. And note that orientation-preserving isometries on a hyperbolic plane are exactly Mobius transformations. Now we define a modular surface. A modular surface is a quotient of hyperbolic plane by PSL to Z. So it's defined over here. And note that this PSL to Z is generated by two elements, 1, 1, 0, 1, and 0, minus 1, 1, 0. And from the first element, it should be denoted by tau. So by Möbius transformation, it is just z plus 1 over 0 plus 1. So this is z plus 1. And when you see the second element, sigma, it transforms z to 0 minus 1 over z plus 0. So z goes to minus 1 over z. So this tau means just translation, and sigma means inversion with respect to the unit circle. Geometrically, a modular surface can be shown as the follows. It's because there is tau here. This may be tau inverse. And this transformation could be seen as an inversion, sigma. So tau and sigma, from tau and sigma, we can see that modular surface can be shown as follows. And since this is hyperbolic, actually this modular surface looks like this. So this point is here, this point is here, and here is the cusp. So let's move on. So from the modular surface, sorry, and by tau and sigma, yeah, this is tau, this is sigma, you can cover the hyperbolic plane from the fundamental domain. Now we move on to the coding of geodesic flow and continuous flexion. There are some lots of relations, and here the word coding means that we want to translate the informations of the given geodesic to the sequence of integers. Here the sequence of integers might be AIs. So wait a second. Please look at the picture. The geodesic gamma is given on the hyperbolic plane, and assume that this geodesic is not a vertical line, so it should be a half circle perpendicular to the boundary. There are two limit points on the boundary. Well, you can think this as intersections, two intersection points on the picture. The left point is called the initial point. And the right point is called the terminal point. Without loss of generality, the x-coordinate of the initial point is between -1 and 0. We can express this coordinate of initial point by using continued fractions, a-1, a-2, a-3, and so on. And this means, wait a second. This would mean -1 over a-1 plus 1 over a-2 over 1 over so on. And the terminal point would mean a0 plus 1 over a1 plus 1 over a2 plus 1 over and so on. Okay, so our main goal in this section is describing any geodesic gamma by using partial quotients a sub I of continued fraction expansion of endpoints. In the picture, we can see this red area, and which is a modular surface. So the geodesics on the modular surface would act like this. So geodesic would go on, and then it would reflect here, go on, go on, go on, and maybe go down again. And when you fold this geodesic, we have a geodesic gamma here. So we denote by this geodesic gamma bar, And since the modular surface is a quotient of a hyperbolic plane by PSL to Z, which is generated by translation tau and inversion sigma, okay? This is tau, and this is sigma. And applying these elements of PSL to Z on the geodesics on hyperbolic plane would not change when we see this geodesic as a geodesic on a modular surface. This is an important fact, and let's move on. So first of all, we apply tau. We use the translation tau, which sends z to z plus 1. Apply tau negative A0 to gamma. So here, the geodesic is tau to the minus A0 of gamma. So the terminal point becomes A1, A2, and so on. So before it was A0 plus A1, A2, and it becomes just A1, A2, and so on. And the initial point, before it was negative A minus 1, A minus 2, and so on. And it translates, and then it becomes minus A0 minus A minus 1, A minus 2, and so on. Now, we want to take inversion here because the terminal point is between 0 and 1. We will take inversion with respect to this unit circle. So we apply sigma. Sigma was inversion, and it takes z to minus 1 over z. Here it's kind of complicated, but this terminal point, when we take inversion to this terminal point, and this terminal point goes to here. So A1, A2, and this point would go to the negative 1 over A1, A2, and so on. So negative 1 over A1, A2 is here. And if we look at the initial point was negative A0 minus quantitative fraction A minus 1, A minus 2, and so on. And if we take sigma here, then this coordinates becomes 1 over A0 plus quantitative fraction A minus 1, A minus 2, and so on. And note that this geodesic flows direction changed. Like before it was going to the right, and after it is going to the left. And when we calculate these new coordinates, we kind of know that this coordinate becomes minus A1 minus quantitative fraction A2, A3, and so on, while the right one, 1 over A0 plus quantitative fraction A minus 1, A minus 2, and so on, it becomes just quantitative fraction starting from A0. So what we have seen so far, so we will please look at the original version here. And the initial point is A negative 1, A negative 2, and so on. And the terminal point is A0, A1, A2, and so on. And the terminal point becomes, it starts from A1, and the initial point is starts from A0. So this, actually A0 was here, but this A0 moved to here. So you can see this, I mean, we obtain a shift map from here. And what's more is that when you go here, this picture represents the zeroth excursion with respect to this boundary. So this picture represents this line. And when you take inversion here, and then this part represents this part, which would be another excursion with respect to this boundary. So when we think of nth excursion, then the coordinate of the terminal point would be am plus conjugate fraction am plus 1, am plus 2, and so on, while the coordinate of initial point would become negative an minus 1, am minus 2, and so on. Maybe it's not really correct, but anyway. So, and what we are interested here is the excursion time. The excursion time is just a length of this hyperbolic length of this curve, and we'll denote this by Tn, and Tn is similar to 2 times log of an. It's because the height, this is the height, and sorry, maybe this is the height, and this height is similar to log of an. That's a hyperbolic distance. So we have the excursion time here now. So let's move on. Okay, we go back to our main question. For a given unit tangent vector v and a geodesic flow g sub t, we wanted to calculate the dimension of the set of fellow traveling vectors w with respect to v. For v, we have a corresponding geodesic, and from this geodesic, we had conjugate fraction digits an, and the excursion time Tn was similar to 2 times log of an. And similarly, for W, note that we have digits Bn, and let the excursion time be Sn, and Sn is similar to 2 times log of Bn. So as you can see in this objective, we want these 2 points, their distance should be bounded by large R. What do you mean by distance? 2 points distance on the modular surface. So here is 1 point, and here is another point. When the distance becomes bigger and bigger, the distance would be similar to the difference of height. Difference of height would be like this red one. That's because this modular surface, the width of this modular surface is bounded by 1. So this distance would be bounded by 1. So only the height matters when distance goes bigger and bigger. So we are interested in height, and we want to make, there are 2 geodesics, and they are going around the modular surface, and their heights should be similar. So it turns out that when we think of V, and please look at this picture, and this picture represents the movement of V, and here there is a red and blue and red excursion times, and through these excursion times, the geodesic would move like, the height would be like this. So if these excursion points here, these 4 points are similar to these 4 points, these 4 points are the excursion points of W, while the former 4 points are the excursion points of V. If each 4 points are similar, then GT of V and GT of W's heights would be similar as well. So the distance of GTV and GTW would be bounded as well. So what we want is that we want to find W so that there exists a global bound such that the partial sum of excursion times, their differences should be bounded by large N. Okay, so how can we construct these kind of W? So assume that V is given. So from V, we can just assume that Ti's, which are the excursion times of V, are also given as well. And we will use inductions. So let's just assume that Si is given for I between 0 and L minus 1. And we'll find some conditions for SL here. So first of all, let's assume the difference between TL and SL is bounded by large N. And we'll do some positive, negative feedbacks. So set SL greater than TL if the partial sums up to L minus 1 of Ti is bigger than the partial sum of Si. If we set SL like this, and then the partial sum of L, their differences would go down. So when you look at the picture, so please look at the picture, if these partial difference of the partial sums are positive, then let SL be bigger than TL, then this would go down. Here, again, still it's positive, so it will go down. Here, it's negative, so it will go up. It will negative go up, positive go down. And as we assumed, this TL minus SL is smaller than large N. So this difference is bounded by large N, so that every partial sums should belong between large N and the negative N. Hence, the difference of the partial sums should be bounded by large N. So here is our main statement. Given AI and BI, where AI corresponds to the given vector V, and BI corresponds to the given vector, corresponds to the vector W. For AI, every AI is given, while for BI, only I between 0 and L minus 1 is given. Let BL be in either an interval AL and e to the n AL, or e to the negative n of AL and AL. And here we have to choose between these two intervals, while this choice depends on the given sequences. Actually, this choice is when you go up. This choice is kind of when, the partial sums, the difference of the partial sums are positive or negative. So that means this choice. And from this condition, we have that there exists some constant C such that the distance between the GT of V and GT of W are bounded by 4 times N plus C. So here are some remaining works. Our main objective was to calculate the Hausdorff dimension of fellow traveling vectors for a given V. So V is given and W is the element of the set. And our main question is the dimension that we like in here, the proposition, we had quantity fraction digits condition, and we also have this distance condition. And our question is that the Hausdorff dimension of these two sets are similar, are same or not? And what we have to do more is that we have to calculate this latter set dimension. So these conditions are not easy to describe, but there are lots of these kinds of results. For instance, Hensley proved that if X is real number between 0 and 1, and its counted fraction digits are between 1 and n, and hence we calculated the Hausdorff dimension of this set En as follows. So okay, thank you for listening. This is the end of my talk.
Thank you very much. Thank you. So, are there any questions for Kangrae, including in the chat? No? Well, if there are no questions, then let's thank the speaker again.